You probably all heard the word bandwidth, right? Say, hey, we don't have the bandwidth. The bandwidth of our internet is not so good. So what does it really mathematically and from a scientific point of view mean? So if we have the magnitude plot of a transfer function, a system versus omega, which is the top portion of the Bode plot, if you plot that, the frequency at which the magnitude drops 3 decibel below the initial value, right? So let's say if this curve starts at 0 decibel, and 0 decibel means what? 0 decibel means the magnitude of the transfer function is 1, right? Because this is 20 log of the magnitude. So when this is 0 means the magnitude is 1. And when the magnitude of the transfer function is 1, what does that mean? Means the magnitude of the output is the same as input, right? Because always magnitude of output is magnitude input times magnitude of the transfer function. So, but when the decibel goes below 0, what does it mean? When decibel goes below 0, it means the magnitude of transfer function is now between 0 to 1. It's less than 1, so the magnitude of output is less than the input. So you have reduction in the amplitude of the signal, right? So how far do we go before we say, well, the signal is not good anymore? Well, the thing that is common convention is 50% of the energy of the signal that you can see here. Once the energy of the signal drops 50%, reduced in half, then we say the signal is not really something that we can rely on. And I don't know if you know it from vibrations or not, but the energy of a signal, so if I have a signal like U of t is equal to A times sine omega t, the energy of the signal at any point, it depends on the energy is proportional to A squared omega squared. Okay, so frequency squared and amplitude squared. So when we say the frequency drop, if we keep the frequency the same, right? We learned that for a linear system, when we pass to it this U of t, right? If this is G of S, the output Y of t is going to be something of the same frequency. The linear system does not modulate the frequency, does not alter the frequency, where the magnitude of the output is magnitude of input times magnitude of the transfer function. That's the magnitude of the output. It has the same frequency but a modified phase, right? Where the modified phase is the phase of the transfer function at that frequency. So you see the frequency of the output and input are the same. The only thing that is modified is the amplitude. So when we say E prime is half of E, it means what? The amplitude prime is how much? How much should you modify the amplitude from here to here to make the energy drop by 50%? Well, 50 means 1/2, and since E is proportional to the square of that, so that is going to be what? The square root of 0.5 times the original amplitude. And the square root of 0.5 or 1/2 is what? 1 over square root 2. So we can write it like this. And if you know the square root 2 and 1 over square root 2, you know this is 0.707. So if the amplitude drops by like 70%, 71%, then the energy of the signal drops by 50%. So now this number means what? If I take log of both sides of this, so 20 log of A prime to the base of 10 is 20 log 10 of 0.707 times A. And you know this is a product. You can write it as an addition of logs. So it is going to be this plus this. And how much is this value? If you calculate it, this is -3. So that's why we say whenever the magnitude of the signal drops by 3 decibel, that means the amplitude dropped by 70% or the energy dropped by 50%. Okay, so that's why we have this number 3 here. 3 decibel means 50% reduction in energy. And so now the terminologies are the frequency at which this 3 decibel drop happens compared to the beginning, compared to very small omegas. That frequency is what we call a cutoff frequency. And the distance between that frequency and very small frequencies, this band, the range from omega of almost 0 to the cutoff frequency, this range of frequency, we call it the bandwidth. Okay, so that's the definition of cutoff and bandwidth. And one important thing is the bandwidth is related to other things that we learn about performance of a system, transient performance characteristics, like what? Like the rise time. So one of the important things is this one, that the rise time and the bandwidth are inversely proportional. So if you change the behavior of G of S by changing what? The damping ratio. So if I make the damping ratio larger, right? So I am going to make the damping ratio larger. What happens when you make the damping ratio larger? You're raising the rise time. In other words, you're making the system slower, but the bandwidth also increases. So the more damping you have in the system, the bandwidth increases. In other words, this drop happens at a later frequency. Instead of this, it's gonna go like this. And here is where you have 3 units drop, and so that is gonna be your new bandwidth. So this is when, if this is zeta 1 and that is zeta 2, can say zeta 2 is bigger than zeta 1. I added more damping. I could get a larger bandwidth, but at the cost of making the system slower. Okay, so these two are inversely proportional. Now, how can you get the bandwidth in Matlab? I'll show you. Also, we learned in the past about resonant frequency and resonant amplitude, right? So we learned them, I guess it was, where was that? Here. So we learn about omega r and mr, resonant frequency and resonant peak value. Is there a way that we can find them also in Matlab for a system? Yes, the answer is yes, we can do that. And the commands we use is, first, we have, in the past we didn't, but now they have added this. There is a command in Matlab called bandwidth, so we can directly apply that, right? So if we look at the system here, 5 times 0.5 s plus 1 and s plus 1, right? So let's look at this system. So if we define that transfer function, we say the transfer function system is the transfer function of, in the numerator we have 1, in the denominator we have convolution of 2 things. One is s times s plus 1, which is 1, 1, 0. And the other one was 0 and, or 1 and 0.5, I assume, right? S plus 0.5. So I multiplied the s by s plus 1, converted it into s squared plus s plus 1, and then now I'm multiplying it by 0.1 and 0.5 and 1. So this has to be this way. So this is the transfer function that we have, and now we can directly run the command bandwidth on it. And it says the bandwidth is nan. Okay, that's quite interesting. What what does it mean? Bandwidth is nan. So let's do the Bode command. So we say do the Bode plot of the system. And if we look at the Bode plot, from the Bode plot, we should be able to find it here. Okay, so this is the Bode plot. It says nan, but that's not necessarily true. So let's go back and look at the definition again. It says the frequency in which the magnitude is greater than negative 3 decibels. Okay? Yes, or 3 decibels below its zero frequency. So if we go back and look at the Bode plot, so here we are at something less than 50 decibels, right? Let's go and check it. So if we use data tips and move the mouse, so at low frequencies, doesn't seem to go any further closer. That's the closest it goes for 0.02. So it is like 34 decibel or so, although we can zoom into that area and see it. This one says for that, but if we can zoom in into here, you see that the actual thing is like 43 decibels or 42 decibels. So once we go down 3 decibels below it, which is like 39, wherever we are at 39, that should give us the bandwidth. Okay, and here you see it's already 34, so the bandwidth is really small for this system. Okay, it is quite small, but if we can somehow find the frequency corresponding to like 39-ish, then we can say, we can do that. We can just insert a line here at almost 39, a horizontal line, and see where it cuts the graph, right? Something like this, I would say. To make sure this line is horizontal. And if you want, you can always connect it to the other side to make sure. So this is a little better if you do it like this. And exactly wherever it hits, right? So you can use another line and project this down here. And you see this is roughly around 0.11 or so, a little more than 0.011. So that is the bandwidth, okay? So it's a low bandwidth, but you can try another system. So this system is, and that's why probably it returned nan, because it could not zoom in to this, and you see that the smallest frequency I had was 0.02 and the bandwidth was less than that, so it could not find it. So nan here means really I couldn't find it. But if I change this to something a little simpler, maybe this one, let's see if this one does any better. So if I go bandwidth with this, again, that's none. Let me change the transfer function to something different. There we go. Okay, it's about 2 hertz, right? So if I change it to this transfer function, the bandwidth is 2 hertz. And now if again I do Bode plot for this system and I go find that frequency, go 3 decibels below, you see that at about, that is 1, that is 2. This is roughly at 2 hertz where I dropped 3 decibels below the stationary value. Okay, so this is the bandwidth. The other thing that you want to learn is finding the resonant frequency and value, and we get those through the Bode plot. Okay, so we can either directly click on the Bode plot and find it, or we can use the max command. So we can use a fine range of omegas, because again, if you look at this Bode plot here, can I find it from here? Absolutely. right? So this is the peak value, and I use my data tip again and try to find it. But whether I have a value right at the peak or not, that depends on the resolution of the points that I have. So if I say, you see, look at the magnitude, that's -2. So the max value, so it seems like this is the max value. So the frequency at which this is happening is 1.22 radians per second. So that's a resonant frequency, and the magnitude is -2.43. But of course, that is the 20 log of the actual magnitude. So that's not that MR that I showed you here, right? That's MR that you saw here. This MR is without taking log of it. So if I want that value in this system, then I have to convert that decibel, which is -2.43, back into normal. So how do I do it? That's 20 log of that number. So if I raise this, first I divide this number, this -2.43, I divide it by 20, and then I raise 10 to the power of that, okay? This is how you go back from decibel to simple magnitudes. And this is the magnitude, 0.756. So for that system, this MR is 0.706, and I guess from that you can also estimate the damping ratio of that system too, right? Of course, this is a standard second order system, and from a standard second order system you can also calculate the damping ratio, but many times you do not have the analytical model of the system. All you have is a Bode plot that you acquired experimentally. And so from that, then you can calculate all of these numbers and then calculate damping ratio and so on and so forth. So without giving you any physical model, I can just give you a graph, and then from that graph, as I told you in the past, you can obtain a ton of useful information. So that's one way you can get the magnitude and frequency directly from the Bode plots by clicking on it. But what if you want it to be automated without you interfering with the plot, without you clicking on the plot? Is there any way to do it through code directly and you do not interfere? Yes. As I said, you define a fine value for vector omega, you pass it to the Bode command and get the magnitude and phase, and then look at the magnitude. Get the max value of the magnitude, and then get the frequency of the magnitude, right? And then omega at which the max happening is resonant frequency, and 20 log 10 of that amplitude is the resonant peak. So I can easily do that here. And I say frequency is anywhere between, let's say, 0.01, and I can use log space. If you remember, it's better to use log space. So log space of -2 to 2, and maybe 1,000 points. So let's use a lot of data points, and then, oh yeah, there we go. Then here, I already defined the system, so I can use sys and get the magnitude and frequency. And now you run the command max. Now look, I have to remove semicolon. So look at that. Resonant peak is -2.43, which is exactly what we found from the Bode plot. And then the resonant frequency is omega at k, which here you can see that that's 1.219. which is very similar to the 1.2 that we found, okay? So you can do it through this as well, okay? Completely automatically. Good. Now that we have seen these topics, let's start Nyquist Stability Criterion. By the way, before I started, I just added for you this log space command. I mentioned it again in the past, but it's good to see it one more time. And then that formula I just mentioned, that if you want to convert decibel to magnitude, that's the opposite of 20 log 10. You divide the decibel by 20 and then raise 10 to that power. Okay, so I added that to your lectures. So now, what is the Nyquist Stability Criterion? So The Nyquist Stability Criterion says this: I can look at the Nyquist plots of GH, which is the open loop transfer function, and I can tell you whether the closed loop transfer function is stable or not. Okay, and that is a big thing, right? Because if I have this system where G is the feed forward and H is in the feedback, and this output is Y, the input is U, then what we really need to know in order to see whether the system is stable or not is Y of S over U of S, which was G over 1 plus GH, right? So I had to look into the denominator of this. We call this what? We call this the characteristic equation, right? When we set this equal to 0, we call it the characteristic equation. And if this characteristic equation has any root on the right-hand side of the imaginary axis, we say the system is not stable, right? So in order to determine the stability of the system, we have to look at the denominator of what? Of this transfer function. And what was this transfer function called? It was called closed loop transfer function, right? So we have to look at the closed loop transfer function. But now the Nyquist method says you don't need to look at that. All you need to look at is this guy here, G and H multiplied together. So it says now I can tell you, if you just look at the Nyquist plot of this, what we call open loop transfer function, if you just look at the Nyquist plot of that, and the denominator of it, right? So it's a ratio, it has some poles. So if you have the Nyquist plot of that plus the poles of that, I can tell you whether this characteristic equation has any roots on the right-hand side or not. Okay, so by looking at open loop transfer function, you can tell us stuff about the closed loop transfer function, and we use the Nyquist plot that we learned. So how does this method work? Well, this is how it works. So what we do is we define a Nyquist contour, okay, and then we map this Nyquist contour into a new plane called GH plane, and then look at that. So what do I mean by it? This is the part that you need to know complex numbers and mapping of complex numbers. I don't know how in depth you went into complex numbers, but if this is a contour that you define in the S-plane, what is this contour? This contour is a semicircle. It has its diagonal on the imaginary axis and a circle on the right-hand side. And the radius of that is infinite. So literally, this contour contains all of the right-hand side and the imaginary axis of the S-plane. The places that we don't want any pole of the closed loop transfer function to fall onto, right? So the system will be stable or unstable or marginally unstable. So we'll look at this area, and then this contour, we project it into a new two-dimensional plane. We call it GH plane. So at any point, at any S value that we have, it's a real number plus some complex number, right? 2 plus 3i, 4 plus 5i, whatever. We plug each one of those numbers into the open loop transfer function GH, and that would give us what? Another complex numbers, of course, right? And that complex number, we plot it on, again, this complex plane, which now we call GH plane, and that will give us a contour like this. And this is the projection of the Nyquist plot onto the GH plane through the function GH. Good. Now what? Now, first of all, what does this contour have to do with the Nyquist plot that we learned in the past? Well, if you look, this portion of this Nyquist path, so again, this guy on the left side, we call it Nyquist path. This portion of it is what? This is where S is equal to what? J times omega, right? And when I plugged into GH of S, S equal J omega, and then I plotted the polar plot of that, what do we call it? What do we call the polar plot of GH of J omega? Yes, we call it what? We call it the Nyquist plot. So the Nyquist plot is the projection or the mapping of this radius here. What about this one? What does this one do? What is this? What is S over here? S here is also J omega, but omega here is what? Negative. Omega for the top portion is what? Positive. Remember I said that we do not really use negative frequencies in this course until we get to the Nyquist Stability Criterion, which is here. So this portion is again the same as the Nyquist frequency, right? Because we plug in S equal J omega into GH, correct? But we do it for negative frequencies. So I would get again a Nyquist plot, but for negative frequencies. And it turns out that the Nyquist plot for positive and for negative frequencies are the same as each other except for a mirror image. So if this is, for example, this is the Nyquist plot of a system for positive omegas, then if you draw it for negative omegas, it's going to be exactly mirror image of that, something like this. Okay? So all you need is you do mirror image of the omega for the Nyquist plot for positive with respect to the real axis. Mirror image of that will be for negative omegas. Okay? So mapping these two radii into the GH plane is not a big deal. It's just the Nyquist plot and mirror image of that. Now, what about this big arc here with radius of infinity? Well, what is this? How can I write here? S is what here? S, if I call this radius R, right, where R goes to infinity, of course, what is it? How can I write S for this arc? Well, S has a magnitude of R and then has some angle. Let's say call this angle from here to here. If I call it theta, S can be written as R times exponential of I theta, right? Where R goes to what? Infinity, and theta is between what angle to what angle? Negative pi over 2 to pi over 2, right? So I can write S like that for this arc. Now, if I plug this S in to the GH of S, what do I get over here? Well, the thing is, it's a complex number, but the complex number has an infinite magnitude, right? And if you remember or not, if the system is causal, if GH is causal, which means the numerator order is less than denominator, so this GH is causal, and it means that the order of the numerator, so this is like A0 plus A1S plus all the way to AMSM. And this is like B0 plus B1S plus all the way to BNSN, and N is bigger than M. If that's the case, then you plug in for S a high frequency, right? You see here, that's where the frequency is going to infinite, right? When R is infinite means frequency is infinite because that's the frequency plane. So if frequency going to infinite, or here we can say S goes to infinite, what happens? Clearly you see here, my S is going to what? Infinity, because R is going to infinity, right? So clearly here, S is going to what? To infinity. So what happens here? When I plug in infinity into this rational function where denominator has bigger order than numerator, what do you think would happen to this? Yes, it would go to 0. So that whole big arc will be converted, mapped to what? The origin. That's all it is. So how would you map again the Nyquist contour into the GH plane? You draw the Nyquist plot of the GH, you draw the mirror image of Nyquist plot of GH, and then, of course, that whole big arc is just the origin. And so now here you got the contour, you got the mapping of that. So this is the first part, how we get this GH plane contour. Good? Now that we have the GH plane contour, how can we use it to determine the stability of the closed loop system? So this is what we do. So if we have this contour, let's say this is the entire contour, or again, it could be not the entire contour, but the entire contour could look something like this. Okay, so this is one real example where this is the Nyquist plot of this transfer function. This is the Nyquist plot for negative frequencies, and then the big arc is now converted to what? Mapped to origin. So this is the GH plane for that system, right? So now if I have this contour, looking at that, can I tell whether the closed loop system is stable or not? This is where Nyquist says, first, let's learn some terminologies. It says, let's call the number of poles of that GH on the right side of the S-plane P. Okay, so how many poles, the open loop transfer function, right? This has so many zeros and so many poles. How many of the poles of this are on the right hand side? How many poles of GH are on the right hand side? We call those P. We show it with parameter P. N is what? N is the times that this mapped version of GH in the GH plane, that's the number of times this contour is encircling this point -1 and 0. This specific point -1 and 0. How many times do you think that contour is encircling this point in a clockwise manner? So right now, this point is outside this contour. So this contour has never encircled that point. So N here is what? 0. But if you look here, look at here. How many times for this system, we'll go over it in a minute, but for this transfer function where we plotted the GH plane, how many times do you see this closed contour has encircled the specific point -1 and 0? Well, yes, you see it is encircled it 1 times, but what is the direction? The direction does matter. The direction is counterclockwise, not clockwise. N is positive if it's clockwise. If it's counterclockwise, then we say N is what? -1. Okay, so again, if it encircles it in a clockwise direction, it's positive. If it's counterclockwise, it's negative. If it doesn't, then N is 0. So N, again, is the number of clockwise encirclement of the specific points -1 and 0. And then Z is the number of poles of the closed loop transfer function on the right side of the plane, or the number of zeros of the characteristic equation on the right side plane. Right? So Z is the actual thing that we are looking for, right? Remember? All we are interested in that this characteristic equation does not have any root on the right hand side. If it does even have one, the system is unstable. Now, how many are there on the right hand side? How many roots or poles of the closed loop transfer function do I have on the right hand side? The number of roots to this on the right hand side, I call it z. I want what for stability? What is the condition for the system to be stable? Yes, I want z to be 0. I do not want any root on the right hand side. I ideally want z of 0 or negative, right? I don't want a positive number for z. Now, how can I find z based on those two other parameters I mentioned, n and p? N was the number of clockwise encirclement of the specific point, -1 and 0, and p was the number of poles of the open loop transfer function, which I can just look and find out. It says z is equal to n plus p, and there is a ton of proof behind this, of course, but we just right now accepted that z is equal to n plus p. If you want more proof, you can always refer back to your textbook and see it. But that formula gives me z as n plus p. So now, if I go and look at this example with you, again, first look at, there are two systems here. For the system on the left, how many poles for the GH do you see on the right-hand side? Where are the poles for this system? So the first pole here is what? P1 is at -1/T1, and pole 2 is at -1/T2. Clearly, none of them is on the right-hand side. They are both negative. Here we assume the T's are positive numbers. So there is no pole for this open loop on the right-hand side. So the parameter P in this case is what? 0, none. How many times when I mapped the Nyquist contour, this contour, how many times when I mapped the Nyquist contour using this GH in the GH plane, how many times the resulting contour has encircled this point in a clockwise manner? None. So n is also equal to 0, and then the method says z is equal to n plus p, which is what? 0, and 0 means there is no closed loop hole on the right hand side, so this system is what? Stable. So if anybody says examine the stability of the system with Nyquist method, that's how you do it. Now let's look at the system on the right hand side. So the right hand side system has two poles. S, the first one is at 0 and the second one is at +1. Right? And again, remember that P is the number of poles in the right half plane. On the imaginary axis doesn't count, only on the right side. And here the only one on the right side is this guy. So 0 is not considered. So for this system, P is equal to 1. There is one pole of the GH on the right. Now, what about the encirclement? Again, when you plot this GH plane, you see it is encircling the specific point -1 and 0 instead of a clockwise manner, it do it counterclockwise. So n is -1, and z, which is n plus p, is again going to be 0, so this system is stable. I mean, it could be tempting to say, hey, the open loop transfer function has a pole on the right-hand side. That system is unstable. No. This is the open loop transfer function. That does not determine stability. We can never determine stability based on P. We have to do what for this system? We have to form G over 1 plus GH and then look at the roots of this guy and see whether this one has any roots on the right hand side. That is instability, not just GH alone. Here is one that is added would change everything. Okay? Because it brings the denominator of that and will add it to the numerator and will completely change the polynomial. Okay, so please keep that in mind. Again, one last time, the GH alone does not determine stability. It's 1 plus GH that does determine the stability, and the number of poles of that or zeros of that is, when I say zero, I mean root. Let's not confuse you. The number of roots of that on the right hand side is z. If z is positive, then system is unstable. For both of these cases, the system is stable. But let's say if when we did this GH plane, the direction of the circle was this direction. If it was, then n was what? +1. And so this one was what? +2. And then the system was what? Unstable, right? So the direction of this counter and the way that it encircles this specific point, -1 and 0, does matter. Now, a couple of more things. One thing you might wonder, why out of all the points on the S-plane or GH plane, why is it that this point is such an important point? Why should you not encircle that point only? What about the other points? Where do you think that point -1 come from, just intuitively? That comes from the fact that I am relating GH, the open loop, to what? The characteristic equation, which is what? 1 plus GH. What relation exists between these two? How can I convert this to that? How can I convert the closed loop characteristic into open loop? All I need is to add it with the complex points -1 plus 0 j, right? If I add -1 to this, the -1 and 1 cancels, you get this one. That's why you can clearly see that when this is the g of j omega and this is the point -1, when I add these two vectors together, okay, and I add the two vectors together, this one and this one, I get my vector of related to characteristic equation, and so encirclement of this point is so important. Again, if you want more detail on where this formula come from and more about the mapping and everything, you can refer back to your textbook, but you need to know mapping of complex numbers. If I get some time after I'm done with this lecture, if I have a few minutes, I do a very short example of mapping of complex numbers for you. Okay, so I mentioned that. Now, one specific caveat that you have to pay attention to is this, that the Nyquist contour, this guy here, the Nyquist contour should never pass through the poles or zeros of GH, right? So this GH, as I said, it has so many zeros, so it's right k times s minus 0 number 1 times s minus 0 number 2 all the way to s minus 0 number m divided by s minus pole number 1 times s minus pole number 2 times s minus pole number n. So this contour should never pass through any of Z1 to Zm or P1 to Pn. By no means should pass through any of them. And you might say, well, what if it does? Like, for example, if my GH is this transfer function and it has a pole at what? At 0. Well, 0 is here and here is on the Nyquist contour. So how can I bypass that and not pass through it? So I modified the Nyquist contour by a very, very small semicircle around that pole. So I pass through, I do not pass through it, bypass it, by drawing a what? A very, very small semicircle around it, where the radius of the semicircle, I call it here epsilon, and that epsilon is actually going to 0. So it's a negligible thing. And that way I avoid passing through it. And so now you might wonder, okay, how does it affect the G-plane, GH plane? Well, this portion of it is the same as Nyquist plot, no change. This portion of it is again the Nyquist plot for negative frequencies. This big arc, we learned that this one will go to what? Will be mapped to origin. So what about this small circle? Well, this small circle is the opposite of the big circle. I can easily show that because the system is causal. If S goes to 0 instead of infinity, then this small arc here is mapped into what? This giant arc. Where the radius of this giant arc is what? Infinite. Okay, so this small arc will be converted to this giant arc with an infinite radius. And so now you can combine all of those four curves together and get your GH plane. Okay, so that's one thing. By the way, if you remember, again, when we did Nyquist plot, remember that Matlab, when it plots the Nyquist plot for positive frequencies, it also plots the Nyquist for negative frequencies. And I told you, I'll tell you why that is happening in Matlab. The reason is this. It does Nyquist plot so that we can use it for this stability analysis. So not only it gives me the mapping of this portion, it also gives me the mapping of this portion. This big arc by default is origin, so I don't need to do a big deal. Only if I have this exceptional case, then I have to add this huge radius as well. Okay? And that's where there is an S in the denominator of GH. In other words, the type of the system is what? Type 1, 2, 3. It's not type 0 system. There is at least one S in the denominator of GH. Then, when I let S go to 0, the limit of GH goes to infinity, which is this big of a curve. So if I go back here, let me just mention what's the importance of this. So look at this curve here. Look, when the system is type 0, what happens? You have this kind of Nyquist plot, right, for positive frequencies. And then when you do the mirror image of that for negative frequencies, what happens? You're going to get this one. So if you look, the projection of the Nyquist path is already a closed contour. So it can encircle something. But look at here. When the system is type 1, type 2 or so, if I do mirror image, let's look at the system type 1. If I do mirror image of this type 1 system with respect to the real axis, right? So this is type 1 system. This is the graph of type 1 system for positive frequency. If I do it for negative frequency, it would look like this. But now, if you look, this curve formed by positive and negative of omega for a system type 1, this guy here is not completely closed. But when I add that small curve, which is now converted to this huge radius, it will look like this. So now you have this shape here. Okay, or something like that. So it will be entirely a closed contour. So all that matters is this guy is a closed contour. So hopefully I could give you enough info. Now, if you don't mind, I just want to use 1 minute and very fast show you a simple conversion or mapping. So if I say, well, I try to keep it very simple. So this is my S-plane. Okay, and then this is a point here. Let's say it's 1 and 1, right? So this is the imaginary axis and this is the real axis, and my point is 1 plus 1j. And now I use a function gh, which is 1 over s times s plus 2. And I want to know what would happen to it in this new plane, which I call GH plane. So this is S plane, this is GH plane. So all I need, I plug in this S into that function. So what is GH of that point is going to be? Just plug it in. Going to be 1 over 1 plus j times 1 plus j plus 2, which is 3 plus j, right? And if you simplify this, you can use Matlab if you want. So it's 1 divided by 1 plus I or j times 3 plus I. And that is 0.1 minus 0.2i. So it is going to come here. Yes, so that point is GH of S. And similarly, if I have more points and more and more and more, I can project them here, 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 and then this contour will be mapped to this contour. Okay, so this is called complex number mapping. What we do for this stability is we use this contour called the Nyquist contour, and we convert it into the GH plane, and then use that, the encirclement of the specific point, and we look at the poles of it, and then we decide whether the closed loop system is stable or not. Okay, thank you so much. I'll see you in the next lecture.